Yo, what is up guys? So today I want to bring you guys another video about sorting algorithms, and today we're going to talk a little bit about heap sort. So when it comes to its time complexity, on all cases it's n log of n, so it's a pretty efficient sorting algorithm. And when it comes to space complexity, it requires no additional space. If you don't use a recursive approach, you can use an iterative approach, and it's an in-place algorithm as well, because all the transformations we're going to do are going to be done in the original array instead of creating copies of an array like we use in merge sort, for example. And but we're actually going to use a recursive approach in one of the functions we're going to implement called heapify. We're going to talk a little about later on. So you have to consider, in our case, the recursive call stack we're going to use, and we're going to need to use when it comes to creating additional space here. And there are many different implementations of HeapSort. This is the one we're going to be doing here in this tutorial. But all of them are at the end pretty similar, and when it comes to time complexity and space complexity, they're going to be basically the same. So this is the original array we're going to sort today. And the way we're going to do this is to use a data structure called a complete binary tree that we're going to call the heap. So the heap will be represented by our complete binary tree. And we have to find a way to transform this original array, or to treat this original array as a complete binary tree. And this will be a virtual transformation, because we won't actually be creating a binary tree, but we have to treat this array as a complete binary tree. And the way we're going to do this is there's a relation from when it comes to an array in a complete binary tree, that you have a way to find the left child and right child of a given number in the array by getting its index, multiplying it by 2, and adding 1 to find who is the left child of the node, and the right child is 2 times the current index plus 2. So let's have an example here with number 0. So our number 0 will be our parent number, and of course we're starting from left to right, so this will be our first parent, meaning that this is the root of the tree, and its index on the array is index 0. So the way we're going to find the left and right child of number 0 is the following. We're going to get 2 multiplied by 0 and add 1, and this will be 1. So in the array, it's represented by number 3, so the left child of 0 is number 3, and the right child is 2 times 0 plus 2, so this is index number 2, and this is represented by number 8, so the left child of 0 is 3, and the right child of 0 is 8. Moving on, we have number 3. So our parent number now is number 3, so this is a subtree of the original tree, and this is at index 1. So the left child of number 3 is 2 times 1 plus 1. This is index number 3, so represented by number 4 here on the array. And the right child of number 3 is 2 times 1 plus 2. So this is index number 4, represented by number 1 here. And if we do the following with number 8, the parent number, in this case, we'll find a different subtree for number 8. It's at index 2. So the left child of number 8 is at 2 times 2 plus 1, index 5, but the array only has 4 indexes, so this is out of bounds, so it doesn't have any left child, and the same thing will happen to its right child. So we have 2 times 2 plus 2, this is number 6, so index number 6 is out of bounds, so number 8 does not have any childs, so it's alone, it's one of the leaves in the tree, right? So if you take a look at our tree, if you get the idea of we just developed here and generate a tree from it, 0 is the root and has childs number 3 and number 8, and number 3 will be its sub tree, and its childs are number 4 and number 1. So the idea now is that once we have the representation of our binary tree from the array, so this is just how we're going to treat the array as a binary tree, using this relation from current index and left and right child. And from here we have to create something called a max heap. So a max heap is basically a heap that we had before, but all parent nodes must be greater than or equal to its child nodes. So in this case, 0 is not greater than or equal than 3 or 8. So we have to do something about it. And 3 is also not greater than or equal to 4 in this case, so we have to do something about it. And the way we're going to do this, we're going to swap all the elements from down below that are greater than the parent node, and we're going to find a way to push these biggest elements to the top. So in this case, we're going to swap number 4 with number 3. In this case, we have this subtree as a max heap, because 4 is greater than 3 and 1. And now we have to fix this this 0 node here, this first node here, the root, because 0 is smaller than 4 and 8. But in this case, the greatest element here is number 8. So if we swap 0 and 8, we have our original array transformed into a max heap, or this is our first max heap. In this case, the root is number 8, and it's greater than 4 and 0, and 4 is greater than 3 and 1, And 0 doesn't have any childs in this case, so there is no need to compare 0 with anything here. That's why we just leave 0 as it is. So this is our max heap from the original array. And the next step from here is to isolate this number 8, so remove this root, and put it somewhere in the array where we will not use this in our next iteration. So the easiest way to do so is get this number 8 and put it at the last index on the array, because if you convert it back into an array, this will be 8, 4, 0, 3, 1. So this is the array from our max heap, so 8, 4, 0, 3, 1. And now that this is the representation of our original array as a max heap, we can remove this first element as the root, being the biggest element in the array, and transfer it to the last index of the array. In this case, we're going to swap 8 with number 1, and we'll have the following array: 1, 4, 0, 3, and 8. And now that we have our biggest element from the array at the last index of the array, we have to ignore this index from the next iteration because it's already sorted. So now we're going to create a new max heap from the 0th index to size minus 1. And again, we're going to do the same idea to treat this as a binary tree. So from number 1 to number 3, we'll have to create a binary tree from it. So this is our binary tree. And we have to now create a max heap from it. So to do so, we're just going to compare all the elements. So the root here is smaller than 4. So it has a left child is greater than the parent child. So we're going to swap. And once we swap it, we have to recursively check if the swapped element is at its correct position, because it could be this case here where we swapped 4 with 1, but 1 is not guaranteed to be greater than the last element's child. So in this case, the last element's child was number 3, and 3 is greater than 1, so we have to check if number 1 is greater than or equal to its child. In this case, it's not, so then we're going to have to swap again 1 with number 3. And here, we would have to do the same thing. We have to check if 1 is greater than its child. But in this case, we don't have any more childs to compare with. So it means that number 1 is at its correct position. And this is our new max heap. And we're going to do the same thing. We're going to remove the head, swapping with the last element. So in this case, the representation of our array is the following. So we have 4, 3, 0, 1, and 8 that is already sorted. And now we're just going to swap 4 with size minus 1. In this case, with size minus 2. And we have the following array: 1, 3, 0, 4, and 8. And up to number 4, it's already sorted. So from the next iteration, we're going to ignore the number 4 and number 8. So we're just going to create a max heap from number 1 to number 0. And this is our current binary tree. We have to create a max heap from it. We just compare 3 with 1. We swap it because 3 is the largest from these two. And then we have to compare 1 with its child nodes. But in this case, we have no child nodes, so we are done in this situation. And all is left to do is remove the head again. Swap with the last element. In this case, it's number 0. And we will have this following array: 0, 1, 3, 4, and 8, where from number 3 to number 8, it's already sorted. But coincidentally, we have the number 0 and number 1 that are left to sort already sorted, but we'll still have to perform heap sort on them. So next, we're going to create a binary tree from these two elements. So the parent will be 0 and the child will be number 1. And we have to create a max heap from it. So 0 is obviously smaller than number 1, so we're going to swap them. And we're going to compare 0 with its child nodes to see if 0 is greater than or equal. But there are no child nodes, so we just ignore in this case. And this is our new max heap. And we have to remove the head and swap with the last element. And then we have all the elements from the size minus 4 to the end already sorted. And now we have to create our max heap from our 0. So this is our binary tree. So as our binary tree only has the root element, it means that there are no child nodes, and this is already a max heap. So therefore, we just have to put it in its correct place. So we're going to swap 0 with 0 in this case, and it's going to stay in the 0th index position. And this is this final sorted array: 0, 1, 3, 4, and 8. So this is essentially how we're going to approach the sorting of our array using HeapSort. And for this, we're going to use some methods. So as you can see here, every time we're sorting this array, let me go back here a little bit to the start. So the representation as a binary tree is only a virtual. So we are not creating a binary tree structure or data structure. And we have to find a way to transform this initial representation of binary tree into a max heap. So we will have to create a function called max heap. And in order to do so, we're going to create another function, another helper function called heapify, and this is where we're going to use the recursion. So heapify will actually start, given an index, we're going to compare that element with its child nodes and swap necessarily. So in this case, imagine that we're here. We're starting at index number 3 here, at index number 2 because at index number 1 because 0 is index 0, 3 is index 1. So we're index 1 here, and we're comparing with its child nodes 4 and 1. And now we know that 4 is greater than 3. We're going to swap them. And now we have to check if the elements, the child elements where the new 3 position is, if 3 is still greater than the child elements from its current position after the swap, in this case, as this is the last position in the tree, there are no more child elements, we're just going to ignore and return. Otherwise, if we had elements, we would have to recursively call heapify. And this is where we're going to recursively call heapify in order to ensure that every element downstream after we swap an element will be every subarray, every subtree will be a max heap as well. So we can have the whole representation of an array as a max heap. So this is essentially what we're going to do. And in order to do so, we just have to create the code implementation. So let me go back here to the last slide here. So this is our sorted array. And now we're going to move on to the implementation of the heap sort into code. So let's translate all these concepts, all these slides here into code. So let's hop onto the file here. So I've created a file called HeapSort.c. Start off by including stdio.h for printing. And let's also define a macro here called number of elements. This will return the number of elements in a given array, and this will be the size of the given array. The size of the given array divided by the size of the first element in the given array. Oops. And this will return us the number of elements inside the given array. And in here, let's create our main function returning 0. And I'll first create our arrays here that we want to test out, and I'll use the same arrays here. So the first one will be 0, 3, 8, 4, and 1. So this will be 0, 3, 8, 4, 1, 0, 3, 8, 4, and 1. So the same one as the example on the slides. And let's create a second array. This array will be some random elements here. So let's 34, 89, 102, 337, minus 2, minus 78, 3, 1, 9, 7, 22, 34, and let's repeat one of the numbers here. Let's repeat 89. So 89 and 34 are getting repeated. Let's create here a already sorted array for testing. So 335, 336, and 337. And let's create an array with only one element. This will be 337 for test sake. Let's print function here the original arrays first, original arrays, and down here I'm going to create a function called print array that will receive the array and the number of elements inside that given array. And as we have 4 arrays, let's paste it 3 times here. Array number 2, array number 3, and array number 4. This will be 4. Oh, sorry, this is array, right? So array number 4, array number 3, array number 2, and array, and this is number 2. So we're good. Now we have to test the printing function. So first let's create the printing function, define here. So this will be void print array that will receive an array of integers and size of these arrays. Start off by printing just an opening bracket, and down here let's create a for loop. Int I equals 0, I going up to size minus 1 because I want to again print the last element in a separate line in a specific format. And in here I'm going to print the elements within the array as the element, comma, space, and in here print the array of the ith element. And in here I want to print the last element as %d closing bracket and break line, and this will be array of size minus 1. Now that we have our print function created, let's go to the start of the file and create the function definition for it. And we're good. So all we have to do is compile it, gcc HeapSort, oops, sorry, gcc HeapSort, and we just execute it, and the printing function is working as expected. Now let's hop onto the file and finish creating our, let's start creating our HeapSort function. So now let's hop onto line 12 here, let's copy all of these and paste in here because the HeapSort function will have the same arguments as print array. So now we just have to substitute from line 18 to line 21 the term print array for HeapSort. And after that we want to print the sorted array, so sorted arrays will be printed down here. Let me add a break line at the start here again to more easily visualize stuff. And after that we want to print the new sorted arrays, right? So now let's hop onto the creation of the HeapSort function. HeapSort will receive an integer of arrays and an integer size. And here, if you take a look at the slides here, how we're actually sorting is we call max heapify on the full array. That will ensure that all parent nodes are greater than or equal to the child nodes. And after that, we just swap the root node, that is the 0th index, with the last index, right? That's all we do. And then we just call max heapify again on the subarray that goes up to size -1, and we do the same thing. We swap the root index that is index 0 with the current array last index, and we call it again this max heapify on the subarray, and etc., etc., right? Until we reach the index 0 that has only one element, and we keep it at its current position because it's correct. So it's a loop that we're starting at size -1 because this is the last index, right? And we're going up to I greater than or equal to 0, and we're decreasing I. So we're starting at the last index, calling max heapify, and after that, so let's call max heapify. This will receive the array we want to max heapify and the size of the array, and the size here is represented by I, right? But we'll have to change this later. I'll explain why, but let's leave it as I here. And after we call max heapify on the current array, on the current size of the array, so we're considering here with the first iteration, so we're applying the max heapify here on the whole array. We have to swap the first index with the last index. So let's swap the array at the first index with the last index, that is I. So that's all we have to do for now, right? Now let's create this max heapify function, max heapify, that will receive the array and the size. And how does max heapify work? Max heapify will use a function called heapify to help us compare each element from a given index with its child nodes. So if you take a look here at the original array, once we call max heapify, what we have to do is we have to call heapify, and heapify will compare the current index we've passed to the heapify function with the child nodes. But we have to pass an index that has childs, right? It doesn't make any sense to pass 1 here because 1 doesn't have any childs. So we have to find a way that we find the first element or the lowest element on the tree that has childs. In this case, the lowest element on the tree that has childs is number 3. So we have to start passing we have to start calling heapify on the index of 3 here. That is the first index, right? The 0, 1. And after that, we're going to call upwards the heapify function again on the 0th index here. So we can compare now the parent and swap again. So we're going to call heapify here on 3, swap, and then we're going to call heapify here on the 3 minus 1 index. So we're going to swap with 8, and that's all we have to do. But in order to call the heapify function, we have to find a relation between the array and what is the lowest element on the tree that has childs. And that is pretty simple. If you take a look at here, the array has 5 elements. And if we divide the size of the array, that is 5, by 2, we get 2.5. 2.5 we'll get rounded down to 2. 2 will represent the index of the element. So what is the index 2 in this array? So it's 0, 1, 2. It's number 8. And number 8 does not have any child here if you take a look, right? The first element or the lowest element in the tree that has child is the number 8 minus 1 index, right? It's 2 minus 1 index, so it's number 3. So if you get the number of elements in the array divided by 2 minus 1, you get the first element, the lowest element in the subtree or in the binary tree that has elements. So that's what we have to start calling heapify from. So we're going to call a loop. I will start at the size of the array divided by 2, right? Minus 1, right? Because again, this will be 5 divided by 2 minus 1 to get the first element, right? And from here, we want to do this up until the 0th index, and we're going to keep decreasing I. And here, we're going to call heapify function. Heapify will receive the array we want to heapify, or we want to heapify on, the size of the array we want to heapify on, and on top of that, we need to pass the index of the element we want to heapify. In this case, the index is number 3, and this will be represented by I. That's why we're doing this loop. This loop will represent the index we want to heapify currently. So we're going to pass a comma here, or a semicolon here. And we have to create our heapify function now. And to do so, void heapify. It will receive an integer array, an integer size, and an integer index. And how does heapify does this comparison? it will use the concept of left and right child based on a given index. The parent will be the given index. So in this case, we're passing I. I is 3. This is the given index. So this is the parent we want to compare the childs with. And to do so, we have to swap the parent node with the biggest child if any of these childs are bigger than the current element. If not, we're just going to leave it as it is. And for that, we're going to assume the parent is the biggest element. So that's why we're going to create an integer variable called biggest. And this will be equal to I, meaning that the current parent, we're considering it to be the biggest element. We have the left child we want to compare with. So the left child index, if you take a look here, the left child index is the current index of the parent times 2 plus 1. So 2 times I plus 1. This is the left child. And the right child is the current parent index times 2 plus 2. Right? Right child, 2 times the current parent index plus 2. And now that we have the left child index, the right child index, and we're considering the current parent as the biggest element, we have to actually compare and see if any of the childs are bigger than the current element. And to do that, we have to check if it has if this element has left and right childs, right? So if so, to do so, we're just gonna compare it if left child is greater than size, is smaller than size, meaning that we're in bounds, so the child exists, and the array of the position of the left child index, is greater than the array of the biggest element, or the root in this case. So if our left child is greater than our root, we're going to swap the biggest variable to be our left child. But this is not all we have to do. We also have to check if the right child is even bigger than the left child. So to do so, we're going to do the same thing. If right child exists, meaning that it's in bounds, so if right child is less than size, and the array of right child is greater than the array of biggest. Biggest could either be our current root if left was smaller than the root, or biggest could already be our left child. In this case, if you take a look here, we're starting at index 3. So this is our root, and we're saying that 3 is the biggest element in the subtree, right? We're comparing 3 with 4, and 4 is clearly bigger, so the biggest shifts from 3 to 4. So this is the biggest element, and now we're comparing if the right child is greater than the new biggest element. Is 1 greater than 4? No, so we keep it here. But if it was 5, it would change from the number 4 to number 5 here. So to do so, we have to say that biggest will be now right child, if this is the case, right? Child. And we're done with comparing which of these elements is the biggest. And if we haven't found any childs that are bigger than the root, we don't have to do anything. But if we do, this is the case where the biggest is not anymore equal to the I we've passed to the function. So if the biggest is different from the index we've passed to the function, meaning that the biggest is not the root, so we have to perform a swap. We're going to swap in the array the biggest element with the root. So now the biggest element will shift to the root, right? And after we do that, so we're going to, in this example, we're swapping the 4 with 3. And after that, 3 comes down here, right? And this was the oldest, this was the biggest variable, this is where the biggest variable was pointing to. And now we have to check if this has any childs. And if it does, we have to call heapify again to ensure that this new swapped variable is the biggest amongst its childs. So in order to do so, we call heapify on the array again. And the size will keep being size. And in this case, we have to check if what is the index we're passing? The index of the last biggest, right? So I was here and the biggest was here. We swapped, but the biggest variable kept its state pointing to here, to this index. Now we have to check if, what we're doing here, we're checking if this new swapped variable is bigger than its current child nodes. So in this case, it will return immediately because it doesn't have any childs. But in the following case, after we perform the swap, this is the new tree, right? This is the second iteration. We're going to start at number 4 because this has how many elements? 1, 2, 3, 4. 4 divided by 2 is 2. 2 minus 1 is 1. So we're at index 1, 0 and 1. So we will start. You see here that index 1 is the number 4 in the new in the second iteration, and we have to compare 4 with its child or childs. In this case, it's only one child. So we're going to compare 4 with 3 to check which one is bigger. In this case, 4 is already bigger than 3. So we will not perform any swaps, so we will not get in here, right? And then we just ignore this. But once we go to up one level, because we're we're going from the child the lowest child that has elements up to the zeroth index, so in this case up to the root. So we're always calling heap5 from the lowest child up to the root. Once we reach the root here, in this case, the second iteration, we're going to compare 1 with 4 and 0, and we'll get to see that 4 is greater than 1. We have to swap 4 and 1. But in this case, 1 is smaller than 3. So that's why we call heapify again, because in this case, when we call heapify, after we swap 4 with 1, we're going to call heapify pointing to 1, and 1 will compare with its child 3 and check that 3 is greater than 1, and we perform a swap again. And then 1 will go down here, and we will call heapify again in this child, but it doesn't have any childs, right? As it doesn't have any childs, it would stop, and this will return our max heapify, or our max heap, as it is right here. So that's why we have to call heapify again on the biggest element, to ensure that all the elements downstream are always subtrees that are max heap as well. So if you take a look here at max heapify, as I stated before, we would have to change this. We're calling max heapify at our array, and we're passing in the I, but I is the last index, not the size, right? If here we're getting the size divided by 2, and the size is the index plus 1. So if you get, let's compare with the first iteration. This is the first iteration. We're going to call max heapify on. It has 5 elements, but I is starting at size minus 1, so it's 5 minus 1, it's 4. So we're passing 4 here to this max heapify function, right? And we get 4 divided by 2 minus 1. We don't want that. We want 5. So 5 is the current index, the last index plus 1. We always want to ensure that we're passing the size to max heapify function. That's why we're going to add this number 1 here. You could add number 1 here. You could, but for me, it's cleaner to add here and understand that we're actually adding 1 because the I represents the last index and not the size, okay? So that's why we're going to add it here. And last but not least, we have to implement our swap function. That is the easiest part, right? We just have to swap 2 variables. So a void swap that will receive an integer array, an integer x, and an integer y. And int temp will hold the value of array of x. Array of x will hold the value of array of y. And then array of y will be equal to the value of temp that holds the value of x. And we save it, and we're pretty much good to go. Now, the only thing we have to do is create the function declarations up the top of the file. So let's paste here. This is HeapSort, then we have max heap. So let's copy this and paste it here. And after max heap, we have heapify. Where is it? Heapify. We copy this. And we also have the swap function. This is the last function we have to create the function declaration for. And let's just fix this. And we're pretty much good to go. There are no typos, I guess. And let's check if the logic makes sense. So to do so, let's compile it and run it and see if the arrays get sorted properly. So these are the original arrays, and these are the sorted arrays. And if you take a look, it works, right? It makes sense. And let's just ensure, so max heapify is then the heap sort function is sorting these arrays, doing this algorithm under the hood, right? So binary tree, comparing elements, creating a max heap, and popping the roots to the last, and calling max heap again, and popping the biggest element to the end, etc., right? And in order for us to visualize this, we can create a print statement. So this is already working, but I want to visualize this properly to show you. So let's hop onto this, and let's add 2 print statements here. Let's add a print array statement here, the array and the size is, let's print the whole array, right? It makes a lot more sense. And let's copy this, paste it here, paste it here, and let's recompile it and run it, so you can see here what is going on after each iteration. Let me just also add a space in between each iteration here. So let's add a print. Let's add 2 break lines, or one. Add 1 break line between each, and in here, printf. Let's do like this. I guess it's gonna be easy. Let's remove this, save it, compile and run it. So let's check here the first array, or the array from our example. If you take a look here, let's see if the steps are being performed as expected, right? So this is the original array, 0, 3, 8, 4, and 1, right? So 0, 3, 8, 4, and 1. And now the first time we print this is after we call max heapify it, right? So once we call max heapify, we'll perform these iterations, and we have this array here, 8, 4, 0, 3, 1. So 8, 4, 0, 3, 1. And if you take a look here, this is 8, 4, 0, 3, 1. And the second time we call print is after we do the swap. So this is 1, 4, 0, 3, 8. And if you take a look here, after the swap is 14038. So the first iteration makes sense, and it's going accordingly to our algorithm here. The next time, we're going to call max heapify, and we're going to swap 1 with 4, and then 1 with 3. And this will be our array after max heapify, but before the swap. So this is 43018, and here is 43018. And after the swap is 13048. Oh, this is 43018, and now this is 13048, and here it is 13048. So the second iteration also makes sense. And the next one, we're going to call this binary tree. We're going to call again the max heapify. We're going to swap 3 with 1, and this is our new array after the max heapify function, 31048. So here it is, 31048. And next, after the swap is 01348. Here it is, 01348. But as I stated, even though this is sorted, we have to call again the max heapify on this binary tree, and we swap again, calling max heapify, and our next array will be 10348 before the swap. So here it is, 10348 before the swap, and after the swap is 01348. Here it is, 01348. And once we call again at the 0th index, this is a binary tree that has only the root, so it's already a max it's already a max heap. So this will return in the sorted array, because if you print it before or after, this is already the sorted array. So here it is. So 01348, this is the final sorted array, 01348, 01348. So we ensure that even though we were actually performing the sorting, now we ensure that we're performing the swapping using the correct algorithm. It's performing the correct steps between each iteration. So this is basically HeapSort. It can be kind of tricky and to understand. It can be kind of confusing, but if you follow the steps, if you understand what you're doing under the hood, that you're treating your array as a complete binary tree, and you're doing this performing max heap, and you understand how you're performing the max heap, and you're ensuring that the steps make sense with the algorithm you've drawn here on the board, you're actually performing HeapSort. So this is essentially HeapSort. You can take a look here at the other examples, at the other arrays. So this array is really big. That's why it has so many print. But at the end, it will be sorted. So -78, -2, 1, 3, 7, 9, 22, 34, 34, 89, 89, 102, and 337. And the already sorted array, if you take a look here, we keep it sorted at the end, but we also apply max heapify here, and the biggest element pops here, and then we swap with the smallest element, and then again the biggest elements pop here, and then we swap with the smallest element, and we do the same. And the one that has only one element, we just return the element because there's no need to compare with anything, and then we have the final sorted arrays. So this is essentially HeapSort. I hope you understood. I tried to be as detailed as possible in order for you to understand what we're doing, how we're transferring these concepts from the slides here into code, and visualizing each step. So you can ensure that at each step that we've drawn on the board is actually being performed here on the code. And I'll be bringing more videos about algorithms and data structures in the future. And if you have any questions, leave in the comments down below. Thanks again for watching, and I'll see you in the next video. Peace.